All right, Calculus 1. So we're back. We're going to look at section 5.6 today. It's over what's called L'Hopital's rule, and should be one of our shorter lectures, actually. There's not much to it. Let me erase this, though. So this was L2 class that I was just recording for. All right. Differentiation. Okay. All right. So like I said, this is section 5.6. L'Hopital's rule. And to start this out, so I'll just write up one of the problems that they're gonna ask. So you'll see, we're gonna go back and look at another way to do some problems that we did earlier in this class. And actually, so literally, so problems we did earlier slash problems we just looked at in that last lecture. So this all connects back to limits. So, but let me write the problem up. Let's see what I'm talking about. So for instance, let's look at something like this. This is question 7, their exercises. You want to find the limit as x approaches 4 of the following function. B times x minus 4 over x squared minus 16. So when we were learning limits earlier on in the class, one of the things we talked about is sometimes, so generally with limits, as long as the number that they're asking you to plug in, so when we have some number that we want to find the limit, at that x value, as long as that number doesn't give us a discontinuity, then we just plug it in and we write the y value that we know for continuous functions outside of their discontinuities, the limit matches the y value. But at their discontinuities, then we have issues. And so we spent a decent bit of time looking at, well, for instance, here, if x equals 4, if I plug it in and it gives me 0 over 0, then what do I do? That function. So that was the particular situation that we'd see. When we were going through those sections, I kind of highlighted two different kinds of discontinuities: the removable discontinuity, the hole in the graph, which is when you get 0 over 0, and then also when you get a vertical asymptote, and we kind of looked at evaluating the limit there. So what we're going to do is we're going to look at this situation where we get 0 over 0 again. And basically what I'm gonna say is, now that you know how to take derivatives, there's an alternative way to figure out your limit. So again, all we're gonna do in this section is give you an alternative way to figure out limits that you already figured out before. But now that we know how to take derivatives, it actually kind of might make this easier for you. So the first thing I want to do with this problem, though, just to confirm, so that is the situation we're looking at here. So if you factor out the bottom, get x plus 4 times x minus 4. So notice when you plug in a 4 here, you are going to get 0 over 0, which is again a hole in the graph, which means there is a limit, but you can't get it by plugging in the number. So what we learned earlier in the class was, for a rational function like this, all you really had to do was cancel out your common factors and go, and plug it in and go. But it ends up, so this is something called L'Hopital's rule. So L'Hopital's rule says when you have certain types of discontinuities or certain types of, actually, let me look at the vocabulary. There was one particular piece of vocabulary that I used that I like. Well, they call it indeterminate forms. So again, that's what we called it in college algebra as well. So when you have 0/0, that's an indeterminate answer. And we'll kind of talk about, there's actually one other indeterminate form, at least that we're gonna teach for, yeah, one other indeterminate form that we can use this for. So L'Hopital's rule says when you have an indeterminate form. So right now we'll just read that as when you have 0/0, then you can actually find the limit of this by, so the limit as x approaches 4 of this is the same as the limit as x approaches 4 of the derivative of the top divided by the derivative of the bottom. So basically what L'Hopital's rule says is if you've got two functions divided like this, two functions divided, you're trying to find a limit, you're getting something like 0/0, then you can take the derivative of the top and the derivative of the bottom, and then replug the 4 in. And if that works out, that limit matches the limit of the original function. Basically, the limits match after taking the derivative, but only at those, only at the x values that give you these indeterminate forms. So in this case, only at an x value that gives you 0/0. On this function, this is only going to work for 4. But what we can do is we can just take the derivative of this and take the derivative of this, take them top and bottom, and then reevaluate this. So let's do that really quick. Actually, I'll have you guys pause on your side. I'll pause on my side since, again, you guys are work well with derivatives. Go ahead and take the derivative of the top, derivative of the bottom, and let's see what we get. All right, so then on the top, when you take the derivative of the top, what did you end up getting? You should get a 3. When you take the derivative of the bottom, what do you get? That should be a 2x. Notice when you plug in 4 there, you end up getting 3/8. So what we're saying is that's the limit as x approaches 4 of my original function. And notice that matches the result we got again earlier in chapter 2. You cancel out the x minus 4 over x minus 4. End up with 3/4 plus 4, which is 8. Still end up with 3/8. So this is now an alternative method for us to find these limits when you would normally get 0/0 when you're trying to find the limit. That it basically makes it so we don't have to do factoring or anything like that. So this works. This works well, actually. Let's practice this for a second. So, well, let's practice this. So let's say if on 15, I want to find the limit as x approaches 3, and this is of, or that would be something squared minus 2x. So on top we have x squared minus 2x minus 3. On the bottom we have x minus 3. And again, we could do some factoring and try to play with that. But L'Hopital's rule is saying instead of that, I could just take the derivative of the top, take the derivative of the bottom, replug in the 3, then see if that and then see if that gets me an answer from there. But whatever, but if I do get an answer, then that answer is my original limit. So go ahead and run that through. Take the derivative at the top and the bottom, plug in the 3, let's see what we get. All right, so easy enough. There's really easy derivatives. So this is the same as the limit as x approaches 3 of on the top. You would taking the derivative. What did you get? You should have got 2x minus 2. On the bottom, what's the derivative? That's just a 1. You plug in the 3 here, what do you get? 4. Perfect. That's our limit. Now, in fact, this method works so well that, so these first two examples were rational functions. And again, we can easily see where rational functions get 0 over 0 because we can factor, we can look at where the common factors are. But this method works so well that it works on other functions where they aren't, maybe they are rational functions, but even if they aren't rational functions, you're going to end up getting 0 over 0. So it works on any function where you get a 0 over 0 situation. So, and that's the kind of the point and the power of L'Hopital's rule is it's saying, I mean, maybe this is great here, maybe this saves you some time, maybe it didn't, but there's plenty of other situations where when we try to find the limit, we get 0 over 0, and in every one of those situations, all you ever have to do is take the derivative. Oh yeah, take the derivative kind of the top and bottom and go from, or yeah, take the derivative and go from there. So for instance, let's look at something like 9. 9, we want the limit as x approaches 6. The square root of x plus 10 minus 4 for x minus 6. And so now this is still, I mean, this is like a little bit like we talked about in the last lecture. It's not exactly a rational function because this is not a polynomial. But nonetheless, we see exactly where we're getting the 6 in the bottom. But notice again, there's no factoring you could do up top to kind of figure out why the top is becoming a 0 when you plug in 6. Therefore, so this definitely, if you wanted to take, so in chapter 2, when we looked at a limit as x approaches 6 for something like this, we had to do some complicated thing with square roots and conjugates to get this in a form algebraically where we could eventually cancel something out and then plug in the 6, right? So it took a good bit of work. What we're saying here is even in a case like this where factoring ultimately doesn't do anything for me, and the algebra that we have to do is kind of long and takes some time and work. So especially in a case like this, all I got to do is take the derivative of the top and the bottom and plug in the 6 and go. So again, notice too, like I said, you easily see why the bottom is 0, but the top happens to kind of work out to 0. 6 plus 10 is 16. Square root of 16 is 4. 4 minus 4 is 0. So again, as long as you try to find the limit, you're plugging in a number and you get 0 over 0, then L'Hopital's rule says take the derivative top, take the derivative bottom, plug it in. Let's see what we get from there. So that's what we need to do. I need you to take the derivative of the top, the derivative of the bottom, plug in 6, and let's see what we get. So go ahead and work on that for a second. We'll come back to it. Awesome. So taking the derivative on the top. It's really just this part that so taking the derivative of the -4, you get a 0. So this is gonna be the same as limit as x approaches 6 of, and on the top, technically you have one function plugged into another, so this is kind of chain rule. So you're going to take this, think of this as x plus 10 to the 1/2 power, so you're gonna do your overall derivative as a power function pattern. Then you're gonna multiply by the derivative of x plus 10, but what is the derivative of x plus 10? That's 1. We're really just gonna take x plus 10 and we're gonna bump it up from a 1/2 power to a 3/2 power, then divide by 3/2, so multiply by 2/3 in front of that, so it'll be 2/3 x plus 10 to the 3/2. And then what about the bottom? What's the derivative on the bottom? That's just a 1. Yeah, I don't even really need to write another line. And then we can plug in 6 and see what we get. Plugging in 6 plus 10 is 16. Again, remember with exponents, when you have a fractional exponent like this, the bottom means your roots, the top means your power. So we're going to take 16 and do the square root of it. And what's the square root of 16? That's 4. And then what's 4 cubed? 4 times 4 times 4. That's 64. 64 times 2 is 128. So this all ends up being 128 thirds over 1, which doesn't change that. So it ends up being 128 thirds. And again, how much easier was that than multiplying top and bottom by square root of x plus 10 plus 4 and doing the bunch of algebra from there? Hell of a lot easier, right? So L'Hopital's rule, crazy useful, actually. And we can keep using it in any scenario. So again, the point is any scenario that gives you 0/0, this works. So let me maybe throw one more in here and then we'll look at other scenario where L'Hopital's rule works. Sorry. Well, first instance. Second, let me figure out this. Look at a couple more. Getting the numbers on these. This is 12. The limit x approaches 0. Sine 6x over 4x. And hopefully too, this kind of jogs your memory of, so again, when we were doing those limits in chapter 2, we kind of had, there was the one limit we learned where it's the limit as x approaches 0 of sine of x over x, and we said it equals 1. And we kind of, I told you then it would take some geometry to prove that we just kind of didn't have time for in this class. So the interesting thing is if you played that out using L'Hopital's rule, you'd actually be able to confirm it using L'Hopital's rule. So this gives us another way to kind of confirm so that those 2 or 3 different limits in chapter 2 that I just said, hey, just trust that this is the answer, right? You can actually now prove that those are the answer. But anyways, so limit as x approaches 0 of sine of 6x over 4x. So notice that if you plug in 0 here, we end up doing sine of 0. And what is the sine of 0? That's 0. And what is 4 times 0? 0. So again, a 0 over 0 situation. So L'Hopital's rule says, hey, take the derivative of the top, take the derivative of the bottom, replug it in, see what you get. So that's what we're going to do. So let me have you guys run through this. All right. What did you get for the derivative of sine 6x? So for that, you should have got derivative of sine is cosine, and then this is chain rule. You got to multiply by the derivative of 6x. So it's going to be 6 cosine of 6x on the top. And what's the derivative on the bottom? That's 4. Now let's plug in 0 and see what we get. So you plug in 0, 6 times 0 is 0. What's the cosine of 0? That's a 1. 1 times 6 is 6. So you end up with 6 over 4, which is 3/2. The limit as x approaches 0 of sine 6x over 4x is 3/2. And this works so well that it even deals with situations. Let me give you another. It deals with situations like the following. (19) is the limit as x approaches 0 from the right. That just has to do with the domain restrictions there. I think they plug in anything left of 0. Well, no, maybe. I think this just has a vertical. For some reason, just 0 from the left. Either way. So we have on top e to the x minus 1 plus x. I'm not sure why they left that in parentheses. On the bottom, x cubed. Now, definitely, again, something like this. Now we're just out in good la la land, but we're out in la la land. I definitely can't factor anything. It's not as square, like there's no way to relate to what in the world this looks like as far as a graph, or try to deal with algebraically figuring out, some sort of algebra so that I can factor out something eventually and plug it in, right? So this is actually a good example of a problem that I don't want to say it's impossible algebraically, because just because I haven't seen it done or can't imagine it being done doesn't mean it can't be done. But likely this is impossible algebraically. There's no way to actually break this down algebraically. But so especially in a circumstance like this, L'Hopital's rule is beautiful, because again, anytime I get 0 over 0, L'Hopital's rule says I can solve it. Take the derivative of the top, take the derivative of the bottom, plug it in. So, and notice that you do get 0, 0. So we obviously get 0 on the bottom, but even on the top. So e to the 0 is 1. 1 plus 0 is 1. 1 minus 1 is 0. So plugging in 0, we get 0 over 0. So we're going to take the derivative. Let's work this through. So what's the derivative of e to the x? That's e to the x. What's the derivative of this 1 plus x? That's 1, so we basically end up getting minus 1 there. So the derivative on the top is e to the x minus 1. What's the derivative on the bottom? So that's going to end up being 3x squared. I'll go back on 9, guys. I'm really sorry. I did the derivative wrong there because I was teaching a Cal 2 class before this, and I gave you guys I used the pattern for taking an integral. I'm sorry. So we'll go back on 9, but let me finish this through. All right. So now you want to go back and plug in 0. Let's plug in 0 and see what we get. Notice that if I plug in 0 here, what's e to the 0? That's a 1. That's 1 minus 1. That's still unfortunately 0. And even on the bottom, 3 times 0 squared, what is that going to give you? It's also going to give you 0. Sure. Not that that doesn't present any issues. I'll kind of tell you how we're going to deal with that, but let me. So what that means is now we have, so again, what L'Hopital's rule really, is saying is the limit here is equivalent to the limit here. So if we can't figure out the limit here, but we can figure out it here, then we're good. They're equivalent. But now we have another situation where you plug in 0 top and bottom and you get 0 over 0. So we can keep going down the rabbit hole. We can take the derivative again, plug in 0 and see what we get. We can keep doing that as far as we can down until we actually get a result for plugging in the 0. Because again, L'Hopital's rule just says you see 0 over 0, take derivatives top and bottom, and whatever you get out of that new limit is equivalent to the limit on the old function. Or how many old functions we have to go up. So we can run this again then. We can take the limit as x approaches 0. Now I can take the derivative top and bottom, getting 0 over 0. What's the derivative on the top? That's e to the x. What's the derivative on the bottom? It's now 6x. When we plug in 0 here, what do we get? Top, you're going to get a 1. On the bottom, you're going to get a 0. And what's 1 divided by 0? That's impossible. It actually means infinity. It's in terms of limits. So the limit there is infinite. But if we had gotten 0 over 0 again, we could have done that. We would have just done L'Hopital's rule again. So again, L'Hopital's rule just says, like I said, it's like going down a rabbit hole or a Russian nesting doll. The limit as x approaches 0 of this is equivalent to this, is equivalent to this. So no matter how many times it takes you to get down there, you're going to eventually hit one of these where you actually plug in the 0 and get a result. That's your limit all the way back up. Now, I'm really sorry, guys. Let's go back to the derivative here. I got this wrong. So this was x plus 10 to the 1/2. The power rule says, so this is going to be 1/2 x plus 10 to the negative 1/2. Sorry. Over 1. So then we can start plugging in our numbers. That's my fault. So you plug in a 6. 6 plus 10 is 16. So 1/2 is a square root. Negative just means it's on the bottom of the fraction. So we're going to do the square root of 16 and then put whatever that is on the bottom of the fraction. What is the square root of 16? That's a 4. So then that'll be 1/4 times 1/2, which is 1/8. So overall, this is number 9 is actually a 1/8. And I'm sorry about that, y'all. At the least, accidentally and in error, I gave you guys a sneak peek for Calculus 2. In Calculus 2, you learn about integrals, and spoiler alert, integrals are the inverses of derivatives. Whatever patterns you have for derivatives, for integrals, and Cal 2, you're going to look at how to reverse those patterns, because integrals will just have the reverse of those patterns. I'll look at the reverse of those patterns. All right, so still overall, you get 0 over 0. Use L'Hopital's rule, even if you have to use it multiple times to kind of get down to somewhere where you can do a calculation, and you plug it in, you get your answer. L'Hopital rule also works when you get infinity over infinity. And we didn't talk about that as much in chapter 2, but we did a little bit, I think 1 or 2 problems. But you've probably also seen that. You've just seen that in previous classes. You've actually seen it with rational functions. But there, in the last lecture, we looked at the limits as x approached infinity, and on a rational function, it was common, so you think about polynomial on the top, when you plug in infinity, you get infinity, and in the bottom, when you plug in infinity, you get infinity. So that's actually a situation we're looking at. We're looking at two functions. In a rational function, you're looking at two functions that as you go out to either positive infinity or negative infinity, they're both growing, right? They're both either going positive infinity or they're both going negative infinity. And so when you divide them, the kind of the question is, well, what do you get? That's another indeterminate form, kind of like 0/0, where and I'll leave that term. I'll just leave it as indeterminate. There's a little more mathematically you have to show there to kind of relate it to 0/0. But it's an indeterminate form. What is infinity divided by infinity, right? It's not one because those are not hard numbers, right? So two things are getting really, really large and you're dividing. What's happening to that ratio? Is it staying about one? What is it doing? So it ends up L'Hopital's rule also works for that situation, infinity over infinity. So it gives us a way to get the exact limit in situations like that without having to mess with algebra. We can just use derivatives to get there. So for instance, let's say we had something like 13. I want the limit x approaches infinity. Top, we're gonna have 5x squared, it's 3x plus 1. On bottom, we have 3x squared minus 5. So notice we have a rational function and I want the limit as x approaches infinity. So not only were we just looking at this in the last lecture, but again, notice that you already know the answer to this because it's a rational function and you know from college algebra what the answer is here. From college algebra, we know that as you go out to either positive infinity or negative infinity, for a rational function, if the powers match, then what's my horizontal asymptote going to be? My horizontal asymptote is 5/3. So my limit as x approaches infinity is 5/3. And we kind of reiterated that again in that last lecture. Last lecture, we were looking at limits at infinity. We basically said it's really just all rational functions. You actually just relates all back to rational functions. Those patterns, those rules for rational functions as far as your horizontal asymptotes. So the limit here we know is 5/3. So let's see if L'Hopital's rule kind of confirms that for us. So again, what L'Hopital's rule is saying is, now if you think about actually plugging in infinity, so this is what I was trying to say. You think about actually plugging in infinity to the top. So if I plug in infinity for x on the top, what am I going to get? Infinity. And if I plug in infinity for x on the bottom, what am I going to get? Also infinity. So we have infinity over infinity. Definitely not 5/3. But L'Hopital's rule says anytime you have infinity over infinity for any function, doesn't have to be a rational function, then all you got to do is do the same thing we did on the previous problems. Take the derivative of the top and the bottom, and then plug it in again. So what is the derivative on the top here? Let's see if this works. The derivative on the top is going to be what? 10x minus 3. What's the derivative on the bottom? Good, that's going to be 6x. Now, when you plug in infinity for the top here for x, what do you get? Notice that we still get infinity. What about when you plug in infinity on the bottom? We still get infinity. So after using L'Hopital's rule once, we still get infinity over infinity. But again, L'Hopital's rule says, okay, but I still got infinity over infinity, so I can run this again. So we're going to run it again. Take the derivative of the top and the bottom. And what's the derivative of the top? That's a 10. What's the derivative on the bottom? That's a 6. Now notice, now I have no x's to plug into. So what is my limit as x approaches infinity of 10/6? Exactly, that's 10/6 or 5/3. And that matches exactly what we know, what we got college algebra, looking at rational functions. And again, that pattern from rational functions we saw in the last lecture applies to really anything when we're looking at limit as x goes to infinity or negative infinity. Now we're saying L'Hopital's rule. So as long as not just rational functions, I'm saying for any function. If my limit as x approaches, if my limit ends up as infinity over infinity, then I can use L'Hopital's rule. Same way, work it down, and that'll give me the limit. So for instance, so let's do something that we kind of already knew what that answer would be. Let's do something where we really don't. It's fun. So all right, so yes, so any situation where infinity over infinity presents itself. So actually, let me turn the camera and we'll keep scrolling right on the board. So something like 29 maybe. So the limit x approaches infinity. Here we have, I think it's x cubed on top, have e to the x over 2 on the bottom. So clearly when you plug infinity in to begin with, infinity cubed is definitely infinity. E to the infinity, if you think about an exponential function, it keeps shooting up, right? So as you go to the right on an exponential function, you're definitely going to infinity. So this is infinity over infinity. L'Hopital's rule says I can take derivatives, plug infinity in, just kind of think about the picture of the function as you go out to infinity and see what I get. And if I get infinity over infinity again, then we could even do this again. We could keep going until we actually get a calculation there. So let me see if you can work your way all the way through this. So pause on your side, I'll pause on my side. You can get that. All right, sweet. So the first time through, when you take derivatives, you get 3x squared on the top. And when you take the derivative of e to the x over 2, that's going to be 1/2 e to the x over 2. Right? Now plugging in infinity or thinking about these functions, you're still getting infinity over infinity. So we got to do this again. So let's do it again. You already, and as you were doing this, you already may have had the idea of, so basically you want to think through your derivatives that are coming up and try to figure out, I mean, we need to reach a place where at least one of these doesn't get infinity when we plug it in. So let's see if we can get there. So 3x squared, we took a derivative of that. What is that going to be? That's going to be 6x. This is then going to become 1/4 e to the x over 2. And thinking about these graphs or plugging in infinity, I still get infinity over infinity. So let's go again. When I go again, the derivative on the top is 6. This is gonna be even more, 1/8 e to the x over 2. But now when I plug in infinity, notice we still get a 6 on, we get a solid 6 on the top. We get infinity on the bottom. So we have 6 divided by infinity, or 6 divided by a crazy large number, which gives me what? That's gonna be 0. And that's my limit all the way back up. And it's just always, we can always play it out that way. Let me give you honestly, I think just maybe one more of these just to look at some different functions. Otherwise, we basically got it. Actually, I mean, not that we definitely can look at another one. But honestly, that kind of does the thing. I mean, they're all just going to be variations of that. If you have different functions, you'll see, but you'll get similar results. So again, we've got 0. I think I just did want to see one other but results. Let's look at something like 35. This is probably our last one then. Actually, well, I'll make my own alteration of 35, sorry. So this is not 35 proper. 35 star. This will be the limit as x approaches infinity. I'm gonna flip what they have there, so we'll make it x squared over natural log of x. So I'll give you guys a second to work on this. Pause on your side, I'll pause on my side. Let's see what you get. Sweet. So the first time through, you take the derivative. What was the derivative of x squared? By the way, again, you can kind of confirm, but when you plug in infinity, you're going to get infinity on the top initially. And natural log slowly grows, but it keeps growing as you go across the graph. So that's definitely going to be infinity on the bottom there. When you take the first derivative, or the derivative the first time through, what's the derivative of x squared? That's 2x. What's the derivative of natural log of x? Notice that that's 1 over x, which this is not, I'm not doing the limit again. What I'm saying is that actually, we can do a little simplifying there. Oh, actually, they use an equal sign instead. So dividing by 1 over x just means you flip 1 over x and you multiply. So this actually turns out to be 2x squared. And what's the limit as x approaches infinity of 2x squared? Good. So 2x squared, you go out to infinity, your y values keep going up. And notice also that there's no fraction anymore. So you get infinity out of this, but you don't get infinity over infinity. That means that's our answer. Basically, we can't go any farther with L'Hopital's rule. And it also means that the answer is indeed infinity. The limit as x approaches infinity of x squared over natural log of x is going to be infinity. And so you'll see in a later, like I mentioned on the last lecture with limits and infinity, you'll see at a later point in this, not in this class, but in Cal 2, that there's, we're going to look at sequences and series that converge and diverge. And this is actually going to be one of the things we use to kind of figure out whether things converge or diverge. It's L'Hopital's rule, because it'll help us in some of those scenarios. But otherwise, you got it. That's actually, you guys got it. That's actually everything. So that'll get you 5.6. You'll notice you have 3 other sections this week. But all these sections I'm actually gonna teach as one video. So I'm gonna do them all in one video. And I'm doing that because, I mean, you'll kind of see as we go through it, they're really one whole idea. It's progressive parts, so that's why they kind of separate it into three sections in these calculus books. So it's three progressive ideas, but they really create one whole, just kind of one whole idea. So I'm going to teach it that way. I'm going to teach it sort of as one lecture that gets you to one whole idea. Okay, anyway, so that makes really just one video left for this week. I'll see you guys there for it.